Okay, class, welcome to our second lecture. Today we'll be discussing probability functions, building upon the concepts of sample and event spaces from last time. Let's start with indicator functions. Consider a random experiment with an outcome space omega and an event space script f. The indicator of an event B, where B is an element of script f, is denoted by the indicator of B of omega, which is equal to 1 if the outcome omega is in B, and it equals 0 if omega is not in B. Let's look at an example. Consider the role of a standard six-sided die. The outcome space omega is the set 1, 2, 3, 4, 5, 6. The event space script f can be the power set of omega, script p of omega. Let's define an event O as the set 1, 3, 5, representing an odd outcome for the dice roll. For this event, we observe that the indicator of O for the outcome 1 is 1, and the indicator of O for the outcome 2 is 0. Let's consider some more examples involving indicator functions. Suppose we conduct n trials of a random experiment over an outcome space omega and an event space script f. Let omega n in omega denote the outcome of the nth trial of this experiment. For each event B in script f, we can define an indicator function for event B of omega n equals 1 if omega n is in B, and 0 if omega n is not in B. Then the total number of times the event B occurs in these n trials, let's call this n of B, can be written as the sum from n equals 1 to n of indicator B of omega n. From this, the relative frequency of an event A, this should be B to be consistent in n trials, is simply n of B divided by n. Now, let's talk about disjoint events. Let omega script f be our pair of a sample space and an event space. Consider a sequence of events A, which is an element of script f raised to the power n, meaning A1, A2, and so on, are all events in script f. This sequence is said to be mutually disjoint if the intersection of an and am is the empty set for any m not equal to n, where m and n are in n. If the union over all n in n of an equals the entire sample space omega, then this sequence A is called a partition of the sample space omega. Here's an exercise for you. First, consider the sample space omega equals the set ht raised to n countably infinite coin tosses, and the event space script f equals sigma of an for n in n, where an is the event that omega I equals h for some I in 1 to n, at least one head in the first n tosses. Try to construct a sequence of non-trivial disjoint events within this framework.
Second, let omega script f be any sample and event space. For any sequence of events A in script f raised to n, show that
The indicator of the intersection over n in n of an evaluated at omega is equal to the product over n in n of the indicator of an evaluated at omega. B, the indicator of the union over n in n of an evaluated at omega is equal to the sum over n in n of the indicator of an evaluated at omega if the sequence A is mutually disjoint. Let's examine some properties of relative frequency. First, for all events B in script f, the relative frequency n of B over n is always between 0 and 1 inclusive. This follows directly from the fact that n of B, the count of occurrences of event B, must be between 0 and n. Second, let A in script f to the n be a sequence of mutually disjoint events. Then the relative frequency of their union, n of the union over I, in n of A, I divided by n is equal to the sum over I in n of A, I divided by n. This follows because for a mutually disjoint event sequence, A, the indicator of their union, indicator union A I of omega n, is equal to the sum over E in n of the indicator of AI indicator A E of omega n. Third, for the certain event omega, its relative frequency n of omega over n is always 1. This is because n of omega, the number of times any outcome in omega occurs in n trials, is simply n. Fourth, since the relative frequency is positive and bounded between 0 and 1, it might converge to a real number as n. The number of trials grows very large. The question of whether the limit as n approaches infinity of n of B over n exists is a fundamental concept in probability. Now, we are ready to define the axioms of probability. We define a probability measure on a sample space, omega, and an event space script f by a function p, which maps from script f to the closed interval from 0 to 1. This function p must satisfy the following axioms. First, non-negativity. For all events B in script f, the probability of B P of B must be greater than or equal to 0.
Second, sigma additivity. For an infinite sequence A in script f to the n of mutually disjoint events, meaning AI intersect, j is empty for I not equal to j, the probability of their union, p of the union over I in n of A is equal to the sum over I in n of p of AI.
Third, certainty. The probability of the entire sample space, omega p of omega, must be equal to 1. This leads us to the definition of a probability space. A sample space omega, an event space script f, which is a subset or equal to the power set of omega, and a probability measure p mapping from script f to the closed interval from 0 to 1 that satisfies the axioms, together define what we call a probability space, denoted as the triplet omega script f p. Let's explore some properties that arise from these axioms of probability. First, impossibility. The probability of the empty set, P of empty set, is 0. Second, finite additivity. For any finite collection of mutually disjoint events, in script f to the n a1 through an, the probability of their union, P of the union from A equals 1 to n of ai, is equal to the sum from I equals 1 to n of P of AI. Third, monotonicity. If we have two events A and B in script f such that A is a subset of B, then the probability of A, P of A, is less than or equal to the probability of BP of B. Fourth, inclusion-exclusion for two events. For any two events A and B in script f, the probability of A union B, P of A union B, equals P of A plus P of B minus P of A intersect B. Fifth, continuity. For a sequence of events A in script f to the n, such that the limit of a n as n goes to infinity exists, then the probability of the limit of a n as n approaches infinity, p of limit a n is equal to the limit as n approaches infinity of p of a n. Let's prove some of these properties. We are working within a probability space omega script f p. For the impossibility property P of empty set equals 0, consider a sequence of disjoint events E in script f to the n, where E1 equals omega and EI equals empty, set for all I greater than or equal to the union of all EI is omega and they are mutually disjoint. By sigma additivity, P of omega equals P of omega plus the sum for I greater than or equal to 2 of P of EI. Since P of EI must be non-negative, this implies that P of the empty set must be 0. For finite additivity, consider a finite set of disjoint events A1 through AN. We can extend this to an infinite sequence by setting AI equals empty set for all I greater than n. This new sequence A in script f to the n is mutually disjoint. Since P of the empty set is 0, the probability of the union from I equals 1 to n of AI, which is the same as P of the union over all I in n of AI equals by sigma additivity, the sum from I equals 1 to n of P of AI plus the sum for I greater than n of P of the empty set. This simplifies to just the sum from I equals 1 to n of P of AI. Continuing with the proofs, for monotonicity, for events A, B in script, F such that A is a subset of B, we can take two disjoint events E1 equals A and E2 equals B minus A, the part of B not in A. Since A and B are in script F, B minus A is also in script F. Also, P of E2 must be greater than or equal to 0. Then P of B, which is P of E1 union E2, equals P of E1 plus P of E2 by finite additivity. As E1 and E2 are disjoint, this is greater than or equal to P of E1, which is P of A. So P of B greater than or equal to P of A. For the inclusion-exclusion principle for two events, A, B in script, F, we can write A as A minus B union A intersect B and B as B minus A union A intersect B. Also, A union B can be written as the disjoint union of A minus B, A intersect B and B minus A. From P of A equals P of A minus B plus P of A intersect B and P of B equals P of B minus A plus P of A intersect B and P of A union B equals P of A minus B plus P of A intersect B plus P of B minus A. The result P of A union B equals P of A plus P of B minus P of A intersect B can be derived. The proof for the continuity of probability will be shown in the next section. Let's look at a couple of examples of probability measures. First, consider a single coin toss with sample space omega equals the set HT and event space script F equals script P of omega. A probability measure P from script F to the closed interval from 0 to 1 can be defined as P of empty set equals 0, P of H equals P, P of T equals 1 minus P, and P of the set HT equals 1, where P is some value between 0 and 1.
Second, consider n coin tosses with sample space. Omega equals the set HT to the set of integers from 1 to n, and event space script F equals script P of omega. Let nh of omega be the number of heads in outcome omega, defined as the sum over n in 1 to n of the indicator of h for omega n. Similarly, nt of omega is n minus nh of omega. We can define a probability measure for any event A as P of A equals the sum over all outcomes omega in A of P raised to the nh of omega times 1 minus P raised to the nt of omega.
A good exercise for you is to verify that P, as defined in these two examples, indeed satisfies the axioms of a probability function. Now let's discuss limits of sets, which is crucial for understanding the continuity of probability. First, limits of monotonic sets for a sequence of non-decreasing sets an, where n is in n, meaning an is a subset of an plus 1 for all n. We define the limit as n approaches. Infinity of an as the union over n in n of an.
Similarly, for a sequence of non-increasing sets, an, where n is in n, meaning an contains an plus 1 for all n, we define the limit as n approaches infinity of an as the intersection over n in n of an.
Let's see an example of monotone sets. Consider a monotonically increasing sequence of real numbers an equals minus 1 over n for all n in n. This sequence converges to the limit 0. Now consider two monotone sequences of sets A and B, which are elements of script B of R raised to n sequences of Borel sets. Let an be the closed interval minus 2 to minus 1 by n, and bn be the closed interval minus 2 to 1 by n for all n in n. An is a monotonically increasing sequence of sets, and bn is a monotonically decreasing sequence of sets. We can verify the following limits. The limit of an as n goes to infinity is the union over n in n of an, which is the interval closed from minus 2 to 0 and open at 0. The limit of bn as n goes to infinity is the intersection over n in n of bn, which is the closed interval from minus 2 to 0. Now for limits of general sequences of sets that might not be monotonic, for any sequence of sets an for n in n, we can define the limit superior lim sup and limit inferior lim in f of this sequence. The limit superior of an as n approaches infinity, denoted lim sup an, is defined as the intersection over n in n of the union for m greater than or equal to n of am. This can also be seen as the limit as n approaches infinity of the decreasing sequence of sets formed by the union for m greater than or equal to n of am. The limit inferior of an as n approaches infinity, denoted lim in f an, is defined as the union over n in n of the intersection for m greater than or equal to n of am. This can also be seen as the limit as n approaches infinity of the increasing sequence of sets formed by the intersection for m greater than or equal to n of am. We have a lemma regarding these limits. For any sequence of sets, an for n in n, the limit inferior of an is always a subset of the limit superior of an. Let's look at the proof. For each n in n, let's define en as the union for m greater than or equal to n of am, and fn as the intersection for m greater than or equal to n of am. We can see that fn is a subset of am for all m greater than or equal to n. Consider a fixed n. Then f1, f2, and so on till fn are all subsets of an. More generally, fm is a subset of am for all m greater than or equal to n. This line in the beamer seems a bit off. The previous fn subset am for m greater than or equal to n is more direct. Therefore, we can write that the union over n in n of fn, which is lim in f an, is a subset of the union for m greater than or equal to some fixed n of am, which is en. Since this holds for each n, and en is a decreasing sequence whose intersection is lim sub an, the result follows. Alternatively, let x be in lim inf an. Then x belongs to fn, not for some n not in n. This means there exists an n not in n such that x is in am for all m greater than or equal to n naught. In particular, this means x is in the union for m greater than or equal to n of am for each n in n. Hence, x is in the intersection of these unions, which is lim sup an. This brings us to the definition of a limit for a general sequence of sets. If the limit superior and the limit inferior of any sequence of sets an for n in n are equal, then we say the sequence of sets has a limit. Let's call it a infinity. This limit a infinity is defined as being equal to both the lim sup of an and the lim in f of an. Let's consider an example of a sequence of sets that might have different lim sup and lim in f. Consider the sequence of sets an equals closed interval from -2 to -1 to the n plus 1 by n for n in n. It follows that fn, which is the intersection for m greater than or equal to n of am, is the closed interval from -2 to -1. And en, which is the union for m greater than or equal to n of am, turns out to be closed interval from -2 to 1 plus 1 by n plus 1 if n is odd, and closed interval from -2 to 1 plus 1 by n if n is even. We can then verify the following limits. The lim in f of an, which is the union over n in n of fn, is the closed interval from -2 to -1. The lim sup of an, which is the intersection over n in n of en, is the closed interval from -2 to 1. Since lim in f is not equal to lim sup, this sequence of sets does not have a simple limit. Now we can prove the continuity of probability for increasing sets. Let an in script f for n in n be a non-decreasing sequence of events. So an is a subset of an plus 1 for all n. Then the limit as n approaches infinity of an is their union, the union over n in n of an. The sequence of probabilities P of an for n in n is a non-negative, non-decreasing, and bounded by one sequence of real numbers, and therefore it must have a limit. For it, consider the sequence of disjoint sets a1, then a2 minus a1, and so on till an minus 1, and so on. This forms a partition of the event limit an, which is union an. Also, P of ai minus 1 equals P of ai minus P of ai minus 1 for each I in n, since ai minus 1 is a subset of ai. For each n in n, P of an can be written as P of a1 plus the sum from I equals 1 to n minus 1 of P of ai plus 1 minus ai. This is P of a1 plus the sum from I equals 1 to n minus 1 of P of ai plus 1 minus P of ai. This is a telescoping sum. Now for the limit of an as n approaches infinity, which is the union over n in n of an, we can write P of union over n in n of an by sigma additivity as P of a 1 plus the sum over I in n of P of ai plus 1 minus P of ai. This is P of a 1 plus the limit as n approaches infinity of the sum from I equals 1 to n minus 1 of P of ai plus 1 minus P of ai, which simplifies to the limit as n approaches infinity of P of an. Now for the continuity of probability for decreasing sets, for a non-increasing sequence of sets Bn in script f for n in n, we can consider the corresponding non-decreasing sequence of their complements Bn complement in script f for n in n. Then P of limit as n approaches infinity of Bn is P of the intersection over n in n of Bn. Using De Morgan's laws and properties of probability, this is 1 minus P of the union over n in n of Bn complement. This is 1 minus P of the limit as n approaches infinity of Bn complement. Using the continuity for increasing sets, this becomes 1 minus the limit as n approaches infinity of P of Bn complement. Finally, this is equal to the limit as n approaches infinity of 1 minus P of Bn complement, which is the limit as n approaches infinity of P of Bn. Finally, let's address the continuity of probability for a general sequence of sets. Consider the non-increasing sequence of sets En equals union for m greater than or equal to n of am, and the non-decreasing sequence of sets Fn equals intersection for m greater than or equal to n of am. Both En and Fn are in script f for all n. By the continuity property for monotonic sequences, P of lim sup an, which is P of intersection over n of En, equals the limit as n approaches infinity of P of En. Similarly, P of limine f an, which is P of union over n of Fn, equals the limit as n approaches infinity of P of Fn. From the definitions of En and Fn, we can obtain the inequalities. P of En is greater than or equal to the supremum for m greater than or equal to n of P of am, and P of Fn is less than or equal to the infimum for m greater than or equal to n of P of am. Taking lim sup and lim inf of P of an, we can relate these. The limit as n approaches infinity of P of en, which is P of lim sup an is greater than or equal to the lim sup of P of an. And the limit as n approaches infinity of P of fn, which is P of limma in f an, is less than or equal to the lim in f of P of an. More carefully, we have limit P of en greater than or equal to lim sup P of an and limit P of fn lesser than or equal to lim min f P of an. We also know lim sup P of an greater than or equal to lim min P of an. The provided inequalities on the slide are limit P of en equals lim sup P of an, which is greater than or equal to in f over n sub over m, greater than or equal to np of am, greater than or equal to sup over n in f over m, greater than or equal to np of am, greater than or equal to lim in f p of fn. And then limit p of en equals lim sup p of a, n greater than or equal to lim in f p of an equals limit p of fn. Concluding the proof for general sequences, we know that lim in f of p of an is less than or equal to lim sup of p of an. This establishes that limit an exists, meaning lim sup an equals lim inf an, then p of lim sup an equals p of lim inf an, which means limit p of en equals limit p of fn. This implies lim sup p of an equals lim in f p of an equals limit p of an. Therefore, limit as n goes to infinity of p of en equals limit as n goes to infinity of p of fn. Since p of limit an exists because we assume limit an exists, then p of limit an equals limit p of en equals limit p of fn. This implies p of limit an equals limit p of an. The result follows from these relations if the limit of the sequence of sets an exists. This covers the fundamental axioms and properties of probability functions, including the important concept of continuity. With this, let us conclude the lecture.